Hello, welcome to the first session on acoustics. We're going to be looking at the principles of sound. What I want to do is I want to show you a couple of videos just to introduce sound itself, how we hear as human beings. I want to show you a really bizarre example of the human voice, and then we'll start to take a look at more construction based stuff. We're going to look at how sound is generated. We're going to look at sound through materials, and then we're going to look at what are decibels, anechoic chambers, levels of sound, so on and so forth. And then, of course, there'll be questions attached to this session as usual. Okay, so without further ado, let's take a look at the first video on how humans actually hear.
Have you ever wondered how sounds make their way from the source all the way to your brain? Take a trumpet, for instance. When it's played, it makes sound waves in the air. The outer ear catches the waves, which then travel through a narrow passageway called the ear canal. The sound waves reach the eardrum, which is a membrane roughly half the size of a dime. They make the eardrum vibrate, which in turn vibrates three tiny bones called the malleus, incus, and stapes. These bones amplify or increase the sound vibrations and send them to the cochlea. The cochlea is shaped like a snail and is the size of a garden pea. It is filled with fluid, and the sound vibrations make this fluid ripple, which creates waves. Hair-like structures called stereocilia sit on top of hair cells and are grouped together as hair cell bundles inside the cochlea. The hair cells inside the cochlea ride these waves, and the hair bundles are moved. The hair bundle on top of the hair cell turns these movements into electrical signals. As the hair bundles are moved, ions rush into the top of the hair cells, causing the release of chemicals at the bottom of the hair cells. The chemicals bind to the auditory nerve cells and create an electrical signal, which travels along the auditory nerve to the brain. Different hair cells respond to different frequencies of sound. The hair cells at the base of the cochlea detect higher-pitched sounds, such as a piccolo or flute. The hair cells toward the top of the spiral detect progressively lower-pitched sounds, such as a trumpet or trombone. At the very top or apex of the spiral, the hair cells detect the lowest-pitched sounds, such as a tuba. The auditory nerve carries the electrical signal to the brain, which interprets the messages as sounds that we recognize and understand.
Okay, so that was just to remind ourselves. I'm sure we all knew that anyway. Of course we did. We need to understand that really, so we can see how humans react to sound, respond to sound, and more importantly, it's about the way that pressure works. I mean, without sound pressure, we wouldn't hear anything, and obviously leading to industrial deafness, so on and so forth. Is the level of sound or the magnitude of sound obviously does long-term damage to those very fine hairs within the ear. Okay, let's take a look at the second video. And just to say that I want you to try and disregard the parrot, because clearly the parrot wants to take part in the experiment. And some of that makes me laugh at the end of it is the little girl carrying a glass. She's about 4 years old, but clearly it's her turn next. And I'm sure Mommy has got a little bit of a challenge on her hands. But anyway, let's take a look at the next one.
My name's Chase, and I live in California, and I'm going to try to break this wine glass by only my voice. Mom, look. It will never.
So I did warn you about the parrot, and did you see that girl? Just she was absolutely ecstatic when the glass broke, and of course now it's her turn. Yeah, okay. So we've seen what sound can do. There are a couple of other examples about sound, but I just want to show you some. I don't know if they're fun facts, but let me just show you a few facts about sound that might get you thinking. Obviously, don't want you worrying too much about the black hole scenario because no one can shout at 1,100 decibels, and I shall explain why. Okay, so to understand how sound works, decibels works, I'm going to tell you a story. It's a little bit crap, to be honest, but hey, it's a story anyway. Decibels double or halve every 3 decibels. And Josh is going to do some work with you, I believe, on algorithms. So you convert decibel back to Pascal, back to pressure, and then you do your log, your 10 to the negative log, or log 10, shall I say, and then you convert it back. But to give you some idea about the way decibels work, I want to tell you this. So, once upon a time, there was a king, right, and he had, obviously all kings, they have a princess, so on and so forth, a daughter. So one day, a fierce dragon, terribly gruesome dragon, came along and took the princess away. So the king, not so happy about that, he employs his most fearsome knight of the realm and his trusty steed, and he goes off to find the daughter. So, on finding the dragon, obviously the dragon has his back to him, a fierce battle takes place, and after several hours of fierce fighting, the gruesome dragon is overcome and slain. So the knight goes back to the king with the princess, and the king says, "Ah, oh, that's great, yeah, well done. What do you want?" So the knight said, "A chessboard has 64 squares. I want you to place 1 grain of wheat on the first square and then double it for every square." So as you can see in the image there, there's quite a pile when it gets to square 11. However, the total number of grains equals 18 quintillion 446 quadrillion 744 trillion 73 billion 709 million 551,615, and that is about 2,000 times today's annual world production, and that's a hell of a lot more than the king was expecting. So that's to give you some idea about the way that decibels work, in that they go up very quickly. So if I was to say to you, if you stood next to a jet engine or 100 foot away, that would be just 130 decibels. When you take into account normal conversation is 60, so if I suddenly started screaming and shouting at you, you would expect it to be a few hundred or so, and you certainly wouldn't expect it to be 130. So getting back to the black hole being created by 1,100 decibel noise, you can now see why 1,100 decibels could do that damage if we could actually create that sound on Earth. But decibels are a funny thing. So decibel is actually it's actually 1 bell. It's a tenth. It's BEL, 1 bell. So that's 10 decibels. And the reason why we don't use bells is because bells are too far, they're too great to actually work with. So that's why we use 1 decibel. And you can see some of the human comfort issues here, or not issues. You can see 20 decibels of watch ticking. Have we all heard of watch ticking? Some of you may never have heard of watch ticking because they're a thing of the past. It's all digital stuff now. But the lower the sound gets, the more difficult it is to hear. And if you're working in industry where your job includes sound and you have to strain to hear it, that can be just as damaging as very high sound. And now I've got some occupational deafness personally from working on construction sites. I was tested by occupational nurse and said that I can't even remember which ear it was. Perhaps I wasn't hearing correctly, but working in construction, if you're not wearing the correct PPE, ear defenders, earplugs, and so on and so forth, then it really can do permanent damage. I used to do security. I used to do security at music festivals, Glastonbury, Slane Castle in Ireland, so on and so forth. And I used to be in what was called the pits, and this is down at the front of the stage at the bottom where all the speakers were. And I did a couple of years doing that, and my hearing was probably already damaged at that point anyway. But you know, doing something like that for a living, it's a very short career if you're not following correct PPE procedure. And then you go to painful acoustic trauma where, you know, when you're exposed to extreme sound, that could burst your eardrums, where you've seen in films where you see bleeding from the ears. And you get you can also get things like tinnitus, which is like a permanent irritating noise in your ears. 24 hours a day, drives people insane. It's not very nice. Not that I've had it, but when you look into it and you hear about it and you see and read about it, it is not good. It is not good. Okay, so we've looked at that. We've looked at the decibels. Let's take a look at how sound is actually formed. Okay, so let's take a look at sound waves and pressure waves. Okay, sound pressure and sound waves. There's two elements to making sound. Obviously, we need something to actually instigate the actual sound wave itself, but the sound wave is made up of two parts, and we've got the first thing we have is a displacement wave, and we have a pressure wave, and between the two, that equals a sound wave. Okay, so we need to look at that in a little bit more detail. So I'm going to use a book on a table as an example. Let me draw two books. So we have one book here. Okay, there's one book there. Let's give them a few pages. There we go. Wonderful, wonderful. And there we have the book again, same book again. And there we have the pages in the book. Now, this book sat on a table like so, and in that table there are molecules. So obviously all of the molecular structure of the actual table. So let's represent that like this. So these are the molecules, and they're all, as you can see, they're all uniform. They're all in a state of inertia, so they're not moving, and we can say that they're in a state of equilibrium. Okay, you get the idea. So this table over here was the same table. Now I'm going to do a slight deliberate bump there. Now I'm not going to draw the molecules at this stage with this one, but what I am going to do, I'm going to drop a book onto my table. Okay, now obviously that was quite some sound, and that's picked up, and that's probably if any of you are watching with the sound analyzer on, you'll see that there was a huge red spike, so on and so forth. So we need to look at what happened. So what happened then? So with the book, obviously hit the floor like that. Hit the floor. Hit the table. So again, we've got the molecules here. Now this time, what's happened is that where the book actually hits the table, you can see that the molecules now are all displaced. They're all moving. They're all crushing, condensating into that central area where this is. And as we come back out, like so, we get a bit more uniformity, and then where the table wasn't effective, we go back to inertia in equilibrium. So we can see then, if we take a look at this area here, we can see that there's a condensation where all the molecules are they're being crushed together. Okay, now that's as a result of the energy that was created when the book was slammed onto the table. So at this point here, okay, this point here, we've got an area of high pressure. That's because a lot of pressure has been created instantaneously at the point where the book hit the table, and conversely, there is low pressure. Okay, now all of these molecules have all moved along like this in the same direction as the book did. So, in fact, this is what we call longitudinal. So all the molecules move in a longitudinal way. Okay. Now, let's just focus on this area here, just there. Now, the reason why there's a displacement there, obviously, if we slam the book down onto the table, for the table not to react, so for them molecules to not move, and for the table to instantaneously stop the book, we would need an infinity amount of energy to do that, and there isn't that. We don't have that in the universe. So it's part of Newton's law: for every action there's an opposite and an equal reaction, and that's to say that if you've got a table like this, okay, and then you force down, let's say 8 kilonewtons per meter squared, we're pressing down on the table, there is an opposite and equal reaction of 8 kilonewtons per millimeter squared. So you can see now that when you look at this over here, we can see that there has to be some sort of movement. The table has give way, and the molecules are on their way in a longitudinal fashion, and there's an area of high pressure just here, and there has to be, because of the opposite and equal reaction, something has to give. Now at this stage, what happens is that the molecule, the molecules themselves, they start to return back to where they belonged, where they were in the first place. Okay, now let me just get rid of this bit here. Okay, this, let's just label this correctly. This here on the right, where we've got this displacement, so let's write that. So we've got displacement in a longitudinal way, that equals a condensation. And it's not condensation as we've learned in the last few weeks about relative humidity and so on and so forth. It's just using the term condensation. It's crushed together. Okay, now when this happens here, where we've got the molecules return back to the original state, when that happens, that's called oops-a-daisy, let's get rid of that. Whoop. Yeah. That is called rarefaction. I'm not making this up, by the way. I'm not making that up. You've got a displacement, which is a condensation, and you've got a rarefaction. So what do you think happens next? Okay, so we've got this situation here where the book hit the table straight away, and then all of these return back to the original state as represented over here. What do you think happens then? So what happens is actually these molecules do the same again. So it's like a cycle. So the pressure wave or the displacement wave begins, and then the pressure wave comes afterwards to get this longitudinal frequency, so to speak. So let's take a look at a frequency itself, and we can see better how these molecules have moved in terms of the wavelength. Okay, so I'm sure you've all seen one of these before, sound represented as a wave. So a couple of things about this. We can see the molecules at the bottom represented by these little slashes here. And effectively, if there was no sound whatsoever, the wavelength would look like that. Okay, there's nothing happening. It's only when the book hits the table, then all of a sudden we get this spike in this wavelength of various, it carries various pieces of information. So let's label some of that information. So here we've got what's called, at this point here, it's a peak, and at this point here it's called a trough. Peaks and troughs, okay? Peaks and troughs. Now I'm going to get rid of that a second because we need to focus on something a little bit more relative to what we just spoke about. Now, sound is a cycle, and sound is spherical. It moves 360 degrees like a football. Okay, so when there's noises, a noise just doesn't go generally in one direction. Obviously, if I'm talking in one direction, people can hear me behind. Obviously, when they hear me in front, it's much clearer and louder, and so on and so forth. But it is 360 degrees. Now, so if we look at that and say then, okay, well then this is 90 degrees, that's 180 degrees, then this must be 270, and then obviously we get to 360 degrees. Now what the 360 degrees means is obviously that's the full wavelength. So it's gone through its full cycle. So we can say then that a wavelength, we can take the wavelength at any point. We can just shift this to the right or to the left and just take a section through that wavelength there. That's all that means. And then we start again. So this would become 90 degrees again, 180 degrees, so on and so forth, 270 degrees. So that's the cycle I was talking about. So the molecules that moved within the table, the molecules began to move here. Okay, they began to move there from 0 degrees to 90. Here we've got timeline. Okay, timeline. So depending on the frequency, how high or low the pitch is, depends on the timeline. So a very low sound is going to take a lot longer to get to you than a very high pitched sound, and it also depends on the medium that the sound is traveling through, whether it's gas, fluid, or solid. But anyway, we can see then that here's our molecules along the bottom there. So what happens then? If we look at the previous picture again, this is what I'm going to be referring to at 90 degrees. Okay, so this is what happens at 90 degrees. We're at maximum condensation. And on the left-hand side, you can see you got the rarefaction. This is, so let's just say that. So that's max condensation. Therefore, that would be maximum rarefaction. So when they're incredibly condensed over here at 90 degrees, and then we can see here at 270 degrees that they're absolutely in equilibrium again, and then the whole thing starts again. So we can see this represented like this. These molecules here, the little dots, etc., etc. So if I get rid of those dots now, this is what it would look like. This is what the sound wave looks like. So at this point here, okay, that's at the point of maximum rarefaction. Okay, So all the molecules on the left, let's do that's not very good. That let's move that again. Let's do that again. From here, the molecules are fairly well spaced, etc., etc., and then all of a sudden we get very, very condensed just there. And then what happens to the right of this? Okay, we start to come back out again. We start to open up, and then we get back to maximum rarefaction. Okay, let's just make it a little bit more. My OCD's kicking in there, so it looks a bit better. And then the whole thing starts again. So you can see that there, which is not going to look too great when I've done my drawing. You can start to see that these are starting to close in again on themselves, like so, very condensed through the cycle, and then they start to open out again until we get to the point where, obviously, so at this point here and this point here is maximum condensation, and at this point here and this point here we've got max rarefaction when they all return back to equilibrium. Okay, and we can see that in this following image. So here you can see a typical example of sound being produced across here, and then at this point there we've got the maximum condensation. And if we were to set 0 degrees, 90 degrees, 180, so you get the idea. Well, sorry, it'd be 180, 360 degrees. That's incorrect. Let me just take that out a minute because that's incorrect just there. Obviously, there's our line going across at the bottom. In fact, it wouldn't be there, would it, at all? What am I doing? That's why I've confused myself just there. So let's get rid of that again. Obviously, don't want to give you the wrong idea. That's where we would be. That's 0. We've got our 90 degrees there. And then we've got, obviously, 180 degrees, 270 degrees, and then 360 degrees there. So we start at 0 here, 0 degrees, and then from there to there is 1 wavelength. Because obviously the next wavelength starts at this point and it goes through like that, through 360, returns back to 0 just there. So that's 1 wavelength there. Okay. Now the other thing I just want to show you something that might be a little bit confused, and I do hope you understand this little bit here, because what they refer to here is, if we go back to this, if we go back to the other image, this particular image here, this is the displacement wave. That's the displacement wave. But you don't hear anything from that. That's not what that carries is the information, the peaks and the troughs and the frequencies. So how far apart these are, or how high or low the peaks and troughs are, determines whether it's high pitch, low pitch, so on and so forth. Sometimes you see waves like that, which are very, and then you can see waves like that. Okay, so you got your high pitched here, and then you got your low pitched there, so on and so forth. But what this means here is everything is condensed at 90 degrees there. Okay, 90 degrees, and that's important, and let me show you why. So you can see in this example here about the 90 degrees phase. So again, this is our displacement wave. This is when the book hits the table, and then we have our maximum condensation just there. And this is the pressure wave, and don't forget this is a cycle, it's 360 degrees. What's happening here is that nothing's happened until maximum condensation has arrived at, so all the information needed for the sound wave is there when it tells you how high the peak is, how far the wavelength is apart, how high and low the peaks and troughs are, as I've just said. So once that it starts at 90 degrees there, but by the time it starts to go to rarefaction at this point, look what's happening here. The pressure wave is 90 degrees behind it. So when maximum condensation's occurred here, we get to 180 degrees and everything starts to move back into their place. If we say that maximum condensation there, and then everything starts to move back like that, and then we go to that scenario where we've got the maximum condensation again, etc., etc. You get the idea. So at 180 degrees, the pressure is at 90 degrees. So it's what they mean by that. It's pressure wave is 90 degrees out of phase. Now this is important if you're a sound engineer. They have a term called phasing, and if you don't get your sound frequencies right, certain sound frequencies will cancel out the other. Now this is a very clever way of cancelling sound out altogether. Now there was a factory in Holland many years ago. I believe it was a battery factory, so making batteries, and the residents complained heavily about the amount of noise that was coming out of the factory itself. So what they actually did was they actually put speakers, and they recorded the sound that was coming out of the factory. Okay, so they recorded it, and they would end up, they would see a picture like this, the frequencies and so on and so forth. So what they actually did, instead of the sound being 90 degrees out of phase, they actually put it 180 degrees out of phase. So if you think about that for a second, as the sound was emitting, as it was coming out, the pressure wave would come in where the pressure wave at 180 degrees, so the rarefaction at 360 degrees is where it's completed its cycle, but at 180 degrees the pressure wave is replicating what's about to come again in the form of pressure. So as the cycle continued through the sound, when the pressure started to happen again, the 180 degree pressure wave, meets the new displacement wave at 180 degrees, and it cancels itself out. And it worked. It all but eliminated the noise from the factory. Now I know that's confusing. It can be confusing. And sometimes when I go into this lesson here, sometimes I look at it and I think I have to make sure I know what I'm talking about here, because it does get a little bit. You've just got to think about this 90 degrees. The pressure wave starts at 90 degrees. The pressure wave starts at 0. Okay, but the maximum condensation for the displacement wave is happening here. That's the maximum condensation, but the maximum for the pressure wave is here. Okay, so it's 90 degrees out of phase, because if you look at that there, the displacement wave is already at 180 degrees, so it's 90 degrees behind. But if you put something in there that's half of it, which is the 180 degree, and you throw it back at it, by the time that the sound is halfway through its wavelength, there's another half a wavelength that's coming at it identical, and it's just wiping it out. Okay, so I know it's a little bit confusing. I hope you kind of get your head around that as much as you can. It's not crucially important, but it is valuable information. So we just need to take a look at a few more things. We need to look at sound through materials. We've looked at how sound is generated. So we need to look at sound through materials and in terms of construction and design, and see what we can do about that. Now we know what sound can do. Okay, so taking a look at this image, we can see typically a cross section of a wall. So let's say that's a cross section, and inside here, typically, well, it depends on the specification of the architect, really. If this was, let's say, blocks of offices, and that this partition wall here was what was separating two offices and not necessarily of the same company, then clearly there has to be a particular attention to the way that sound works. So if we look at the incident sound, which is here. Now this could be anything. This could be somebody slamming a book on a table. Could be somebody shouting. Could be somebody dropping something. Could be something dragging something across. It depends on the different type of purpose for the offices as well. So one side of the office could be light manufacturing, and on the other side could be large amounts of privacy needed. It could be a counselling office or something like that. So we've got an incident sound here, there, and we can see that largely sound is reflected off these surfaces there like that. So there's various types of materials that we can use in terms of the build-up of the wall, of which I'm going to set you a little bit of homework in that you need to investigate the types of materials that has different sound absorption and sound barrier. They're two different things, sound absorber and sound barrier. So a barrier is there to try and block out as much or all noise possible. Then you got sound absorber, of which is like a rock wool insulation or something would absorb a certain amount of sound passing through the wall. So we can see here that certain amounts of the incident sound in the left hand office has made its way through the partition. So you can't really eradicate all sound. I mean, you can, but it's going to be very expensive. So we're going to get a lot of reflected sound in the left hand side office. So that's a typical view of what that might look like. So sound itself travels very differently through mediums. Through gas, it travels fast. So we usually use standard pressure, STP, standard pressure at 20 degrees. And that as we talk through the air, sound travels through the air, but it travels a lot faster through liquid and even faster through solid, simply because there's more medium, there's more molecules for the energy of the sound wave to actually pass through. So remember, sound dissipates, it dies off, because eventually the amount of energy that it initially had, I mean, you could have a book that I drop this book now on my table and it wasn't very loud, or I can go, which is very loud. So obviously that sound's going to travel a lot further, and because it's gone through the table, it travels very, very rapidly. So if I was to say to you, if you were at a swimming pool and somebody had a starting gun, now you were lying on your side with your left or right ear in the water and your other ear not in the water. Your left ear would be in a liquid and your right ear would be in a gas, or vice versa. It doesn't matter which one. But as soon as the starting gun is fired, the ear that you have in the water will hear it first. Okay. I remember at school many years ago where we used to have the heating pipes that used to travel all the way around the school and all the way back to the big old boiler, oil boiler. And I used to really annoy people. I used to do this, just tapping my pen on the radiator. Now, I didn't know at the time the effects of that. I just thought it was annoying enough for the people in the class that I was sitting in with. But actually, that travelled, 4,000 meters per second, and it travelled around the whole school literally within a second or so, and it was annoying everybody. And if I keep doing this, it's going to annoy you too. Okay, so the more molecular structure to material, the faster the sound will travel through. And with the gas, as I say, it depends on whether the gas is compressible or incompressible. It depends on temperature, pressure, so on and so forth. So there's a lot of variance in gas itself. And you could say the same of liquid to a degree, but But yeah, so when we're talking about sound absorption and materials within construction, we have to start being a little bit more specific about it. So on the left hand side, you can see a standard metal, what we call gyprock metal partitioning system. I've done many thousands of meters of this in my time. And what you can see here typically are the metal studs. Whoa, I don't know why that's just done that. Let's try and go back. There we go. The metal studs. Obviously, you've got a plasterboard fixed either side of it, and then those plyboard, the wooden sheets in between, they're actually there to take services. So there's probably banks of electrical plugs and shelf fixings and stuff that's going to be fixed in those parts, and that's why those boards are there. But then it'll typically be bit filled with insulation, and that's a bog standard. Now the problem with that is obviously sound is just going to travel straight through that. It's going to pass all the way through the plasterboard, through the screws, through the metal to the other side, and then you're going to get a lot of the incident sound on the inside of this room, as you can see, the room on the left, is going to pass very quickly and effectively through to the other side, which is very undesirable. What we've got on the right hand side, we've got what's called a resilient bar, which is this here. Now that resilient bar, so you can see the gyprock partition over here, the metal partitioning, and then I've just put into highlighted in yellow. You can see this is it here. This is the same metal, but the difference being, the difference being is that it's the actual fixings that we're going to take a look at now. So this is one solution here, where if you think about the metal partition, typically you've got board construction. So on the example we saw before, there's our plasterboard on one side, and there's our plasterboard on the other side, like that. Very nice it is too. And then we've got our studs in between, the metal studs. So the metal studs themselves, they're what we call C-section. So they're like that. Okay, there's our studs like that. Here we go, another stud there. And what I mean by stud is these here. These are studs. These are timber studs. But so this is a metal partitioning stud, and then you would screw obviously through the board, okay, and then you screw into the metal. We should stop doing that. Obviously the other side, there's our screw going through into then. It's just done it again. Very nice. Now what's happening obviously is the sound itself is now traveling. Now I've just gone and lost my I'll try this one more time, then I'm going to get very annoyed with it and give up. There we go. It's just done it again. Very nice. Thank you very much for that. Even better, thanks. Right, so when sound comes, let's say we've got an instant sound coming at the wall like that. Now we're going to get a certain amount of reflection off that surface naturally, but we're also going to get sound that goes through the screw. It's going to transmit through the metal stud. It's going to transmit through that screw and through the board, and then you're not going to get a very loud sound, but it is going to transmit, like I say, through each one there like that. Okay, now that's the big problem we've got. Now you can put insulation in between all the studs and so on and so forth, and that will absorb some sound. But the issue really is with the screws and the board, because the board itself is obviously it's fixed at this point, this point, this point, so on and so forth. So effectively the whole thing is one big solid piece. So you can say that this here is connected to this here and to there, because that's connected then to there because of this transmission through these C studs here, and that's the problem. So when we look at, let me just get rid of that. Now I'll leave that there a second. You can see over here now, Let's try to erase this. And I'm going to draw a plan view of what we can see there. There we go. Wonderful, wonderful, wonderful. Right, so let's take a pen. So now we've got our 2 plasterboards again, which are effectively these 2 plasterboards here. Let's give it a little bit of there we go, lovely, lovely jubbly. There we go. And then we've got our studs, okay, and the studs there, timber stud, bit of timber grain there. Look, how very nice. Look at that, look at that. And then we'd have typically a stud there, and again some beautiful graining. There you go, another stud there, and so on and so forth. You get the idea. So what we've got now, we've got a situation, obviously, where the screws themselves are now, but we're still screwing in. We're still screwing into them, but the sound can't travel through from one side to the other now. Now you're thinking, I know what you're thinking. You're thinking, well, how is this side connected to this side then? Well, first of all, we've got that there, so you've got your timber, typically like that, and then that would be fixed onto what we call the sole plate, like that. So, and then you would have your board obviously fixed either side of that, just there, and then on the other side you'd have your board fixed on that side there. But the difference with this is that and this would be top and bottom of the stud, but the studs in between, in there, there's no sound transmission whatsoever. Now where you do fix the walls together and the studs together, you'd be looking at something like this, where you've got structure-borne vibration. It's got nowhere to go. It's got nowhere to go. So let me just erase this again, and I'll explain what I mean. If you take a look at the actual drawing, once I've finished messing around with this eraser, very good. You can see, obviously, there's the same situation again where you've got the studs and they don't connect to each other. Then you've got this in the green here is a system called resilient bar. Okay, resilient bar. I'm going to show you what that looks like. In fact, if we go back to there, we can see this is the one on the right hand side where this is the resilient bar I'm talking about. So if we go forward, that looks great, doesn't it? That's brilliant. Let me just erase this. So a resilient bar on a normal stud wall, you can still do it. Let's change the ink. Let's change the ink on that. You can still do the C studs, metal studs. Look, this is a plan view. All right, and there's our. Let's put some board in. There we go. Now, no, sorry, we don't want to put any board in. Of course we don't. Let me erase that, because that's not the best example. Let me do it this way. So in color, let's get black. Right, C stud, C stud, C stud. And then what you do is you put the resilient bar in, which is effectively just a thin tin. It's actually tin. You put a thin bar in, and you connect it in. Let's do that color in blue. Okay, so the bar goes, the bar itself is connected to the studs, and then what you do is you fix the board to the resilient bar. Okay, so there's our plasterboard now, but the plasterboard is not actually fixed to the C stud. And in fact, what you can see here is, if I just get rid of my eraser again, you can see that the resilient bar on the left, on the, sorry, this here, this whole bar here where I've just drawn, it's fixed to the studs, but with their special fixings that look like this, and you can see that there's rubber grommets there where the sound is, like sound dampeners. So although it's fixed, here's another example here you can see clearly, and then the resilient bar is fixed through those two parts there, and then the plasterboard is fixed onto that. So the sound, you're creating that kind of situation there, and that kind of situation there where the interior walls are actually not fixed to the outside walls, the exterior walls, and that's one way of stopping sound from transmissioning through a wall. So what we need to do then is we start to need to look at sound through materials. Okay, so what I'm going to do is this is going to be set as a homework. Okay, that you'll be looking at sound through materials. So we need to go through this particular section about sound through materials, or it's actually not the best title that, because we really want to stop the sound going through materials. So we're going to look at sound proofing and sound absorption, because they are different things, of which we'll see. So if we look at the sound absorption, typically light in weight, usually soft materials, sponge type materials, because obviously there's lots of little pockets within the spongy texture where the energy of the acoustic energy can be absorbed. It's good for controlling echo type scenarios. So if we're looking at music studios, theatres, close proximity living spaces, apartments, even lecture rooms in the college. I mean, if we can hear the lecture next door in the classroom next to you, that's not going to be great if you can't focus on the task in hand. When we look at soundproofing, typically that's heavier in weight. If we look at certain things like concrete, glass, marble, polished metal surfaces, even rubber has a very, you'll see in next week's session when we talk about the coefficients of absorption. So we talk about materials with their absorption properties. Even as human beings, we have an absorption property. Typically, if you've can remember when maybe you've moved house, where you've taken all the furniture out, you've taken the curtains down, and then you walk into that room and it's very echoey. Or if you even take a bedroom out of the window and take the bedroom, take the bed out of the bedroom, and then you take out the curtains, and maybe you're changing the carpet, and then the room is really echoey, because it's the surfaces that are left are very hard and they reflect the surfaces, but the sound is not being absorbed as much as absorption material, so to speak. So soundproofing materials, they're hard by nature, and it reflects. And it's important to remember that if we have an environment with lots of hard surfaces, then we're going to find it difficult to control reverberations and echoes. So the message really is a blend of both absorption and proofing offer the best results, along with decoupling systems. So you remember the decoupling systems. Let's just quickly go back here. Oh, hang on a minute. Where are we? Here we go. Now that's decoupling system. You can clearly see that the left-hand side of the wall is not directly connected to the right-hand side of the wall. You can see that there if we was to just highlight that. So we can see that we've got these are not connected to each other, and you can see that this wall here is actually, and including this, is actually separated from the outer wall. And that's what we mean by decoupled. It's not coupled together, it's not connected together. Okay, so decoupling systems, and there, just remind ourselves, was the resilient channels fixed in with those particular brackets where the rubber grommets, they're actually, you can see them just here, they're actually absorbing sound and preventing, effectively, sound is vibration, isn't it? So you can see that particular bracket there being fixed onto the timber, the rubber is preventing vibration from going through there. So all leads to an effective decoupling system. So there'll be questions attached to this one. The questions effectively will be: one, identify two sound absorption materials appropriate for an internal wall. The second one will be identify two materials that you can use for soundproofing on that same wall. So two absorption, two soundproofing, and also propose a decoupling system, what kind of a wall are you looking at? And I don't want you to just use what I've used. There are plenty out there. Investigate and research and understand this, and try and do a drawing, try and do it on CAD if you've got the CAD skills. But you need to give some sort of justification for all of your, so don't just say I identify these materials for soundproofing, these materials for absorption, and this decoupling system. It doesn't really mean anything unless you're going to actually tell me why. Okay, so that's going to that will get you in practice for answering project exam and project questions about justifying your choice. So finally, what I want to do now is leave you with this one question for you to look at, and we'll go over it in the next session when we do Sabine formula. Let me just change this. So here is my golf course, and as you can see, here is the fairway. Well, actually, this is the fairway. Let's give it a little bit of texture grain. So there's me grass, beautiful, beautiful golf fairway. You don't have to have played golf to understand this question. You certainly don't. Let me explain what's going on. So here you can see me. Okay, there's me here, and I love my golf. And obviously I'm fantastic at golf, or that's what I tell myself. And what I'm going to do is I'm going to hit this ball, the little black ball there, with my club, the little white-headed club, okay? And I'm at 0 yards. Okay. I'm at 0 yards. Just there. Now, what we've got somebody that's 300 yards away. Now, the reason why I've said 300 yards is if it was only 10 yards away, the question really wouldn't work, because sound has to travel over distance like anything else, like light, everything. But when we say 300 yards, there will be a difference in rate or pace about the question, what I'm going to ask you. Now, here is one of my fans, one of my greatest fans, obviously. So what they're going to do, they're going to shout, great shot, at the exact same time as I hit this ball, at the very exact time. Now, normally, as you know, you should know now, or should understand, you have a sound wave like this, okay? And when I hit the ball, it might look like that. So we've got our peaks here, we've got our troughs here, we've got the distance between the wavelength, like that, and then obviously we've got time, and we've got the frequency, wavelength, whether it's high pitched, low pitched, or all the usual things that comes with a displacement wave and a pressure wave, which equals a sound wave. Now, the person shouting, that might look like this. Very different, and in real life that's probably the way it works. So the two wavelengths will be very different to each other, but we're disregarding that for this question. I want you to base this question on the following: that when this person, my great fan, shouts great shot, as the moment that I hit that ball, the exact moment, at the exact same spot here, 0 yards, when that sound wave travels towards the person up here, okay, the question is, which sound is heard by this person first? Is it A, the ball being hit, or B, the shout? And state why. That's the most important thing. State why. It's a 50-50, ladies and gentlemen. You can say, well, it's the ball, or you can say it's the great shot. But if you're not going to say why, then it's just a guess. So what I want you to understand is everything we've done in this session, you may have to go over certain parts of this session. There is a massive clue earlier on in this session that will answer that question, or at least help you understand how to answer this question. And it is a bit tricky. It is a bit, it'll probably catch most of you out, but all the information you need to know. In fact, one of it's actual visual. There's a visual part of this. So there's an actual slide. Okay, I'll give you a clue. It's got a picture, 3 pictures in this one particular slide, and it will give you the answer. Okay, so all that's left to say, well, you know what I'm going to say. Answer the question and give the question back